Okay, so our next unit here is the study of force. Here's some common forces. The force of attraction, say, of planet Earth pulling on all objects downwards towards the center of the planet. That's, of course, the force of gravity. And the symbol for that is F for force, and then a subscript G for gravity. Microscopic hills and valleys between an object and a surface interlock and prevent or impede sliding. That sounds like the force of friction. So that's force, friction. Surface pushing up on objects, that is the normal force. Now, normal in mathematics means perpendicular, right? So if this is the surface, then, and here's an object, the normal force is always perpendicular to that surface, 90-degree angle. That's what normal means in this context. The force from a stretched string or cable is called tension. We can call that force tension, or sometimes we'll just call it T for tension. Contact force from an external agent, that's just called the applied force, typically just F. Force of resistance from the air is called the force of drag or air resistance. I guess maybe call it force drag. We won't use that a whole lot. Not a real force, but instead the vector sum of all the forces acting on the object. So that's the sum of the forces, or we'll also write it as F net to stand for the resultant force. Okay, so there is some terminology, some common forces. Now, the force that we're probably most familiar with is the gravitational force, and the gravitational force on an object, otherwise known as the weight is a force in newtons, that's m times g, where g is the gravitational field strength, and m is the mass in kilograms. So weight and mass are not equivalent. Now, the gravitational field varies on the surface of the Earth. It's about 9.81, but it varies over the surface. We'll just take it to be 9.80 for simplicity. The moon's gravitational field strength is about a sixth of that. It's about 1.60. So a 10 kilogram object on the Earth, okay, mass is measured in kilograms. So the force of gravity on the Earth, that would be 10 kilograms. On the Earth, there's 9.8 newtons of force for every kilogram. So multiplying 10 by 9.8, there'd be 98 newtons of attractive force between the planet and this object. If you were to transport that to the moon, the force of attraction between the moon and the object would be considerably less. It would be 16 newtons. So the mass of the object didn't change, it's just the force of gravity that did. Now, Newton's second law says that we need to consider all the forces that act on an object because the net force will make the object accelerate. There'll be an acceleration in the same direction as the net force in direct proportion. The acceleration will be inversely proportional to the mass, or, as we'll write it, net force is ma. Now, acceleration, we have said, is in meters per second squared. If you divide a force by a mass in newtons per kilogram, that's got to be equivalent. Well, it is, because a newton is defined as a kilogram meter per second squared. So dividing that by kilograms, you get an acceleration unit. So let's just make sure we understand what we mean by net force. It is a vector concept. So in this case, where there's only one force, the net force is just that only force acting on the object. Now, force is a vector quantity. It has direction, so we have to specify the direction of this one, and usually just a plus or minus is sufficient. I guess it's really in the positive I direction. Here, where the two forces are parallel to each other, the net force will just be the sum of those two. So it will be 3.7 newtons in the negative j direction, or 3.7 newtons downwards. I'll put that over here. Probably a better place for it there. Okay, so here clearly you'll subtract, because they're opposite to each other, and this is 1 newton in the positive j direction, or plus 1 newton. Here we've got 8, 3, so the net force is 5 newtons, and instead of using plus or minus, you could call it east. Here the up and down forces cancel, but we have 7 newtons to the minus I, or westerly, Now here there's no numbers, we're going to have to do it algebraically. So we're going to subtract. We're told that y is the bigger one, so the net force will be y minus x, and the net force will be directed downwards. So to solve force problems, the first thing to do is to draw all the forces acting on the object. That's called a free body diagram, or as we will abbreviate it, an FBD. So here's a typical problem. We've got a cable, and then there's a load of rock on the end of it, and we're told the rock's 2,000 newtons and that it's accelerating upwards. So what forces act on the rock? Well, there will be a gravitational force of attraction between the rock and the earth. So the earth is going to pull down on the rock. The only other thing that's going to push or pull on the rock is the cable, and the cable will pull upwards, and that's a force that we call tension. So those are the two forces that act on the object. Now, we're told that it's a 2,000 Newton rock. So this is a property of the rock. What property is it? Well, it's in Newton, so it's a force. That must be telling us the weight of the rock. And the other thing we're told is that it's accelerating upwards. Now, this isn't a force, but I will put it on here. I just use a squiggly line to represent that acceleration. It's upwards 3 meters per second squared. Okay, so we've completed the force diagram. Next, because those are the only two forces in the absence of air resistance, next, we want to compare those two forces. And that means try to decide which one's bigger and which one's smaller. Well, we're told it's accelerating upwards. And because it's accelerating upwards, there is a net force. And that net force has to also be upwards. So an upwards acceleration by Newton's second law implies an upwards net force. And if the net force is upwards, that tells us that the tension has to exceed the weight. Now, as soon as we know that the tension exceeds the weight, the implication then is, well, if we want to find the net force, we're going to subtract, because they're opposite, and we're going to take the bigger one and subtract the smaller one. And that will be in the upwards direction. So, a net force equation. Well, what do we know about net force? Well, we know it always equals ma according to Newton's second law. And based on the information that we're given in the problem, we know the net force in this case is the difference between the cable tension and the weight of the rock. So this is known as the net force equation. And for the next several classes, we're going to be considering dynamics problems. And our objective in each case will be to come up with the correct net force equations. Now, the last thing we're asked to do is to actually find the tension in the cable. So having written the net force equation, we will inevitably use it to solve the problem. So we see here's the unknown tension. We're given the acceleration. We know the weight's 2,000 newtons, so really all we need is the mass. And that wasn't given. However, it's pretty straightforward to find because we know that the weight is 2,000 newtons, and so we could just divide by the gravitational field. Sorry, just having a little problems with my pen there. So the mass will be the weight over g. So it's a 2,000 Newton rock, 2,000 newtons of weight, and there's 9.8 newtons on every kilogram. So dividing that, we get 204.1 kilograms of rock. Let's try writing that again. So now we know everything that we need in order to find the tension. So the tension, if we substitute, the weight is 2,000 newtons. The mass we know is 204.1. Let's try it again. Nope. And it's sticking here. I may have to just pause the video and reset the pen. Okay, so hopefully we're back in business now. So it's 204.1 kilograms, and then in the net force equation it's mass times acceleration, so it's 3 meters per second squared of acceleration. So that, multiply those two together, bring the 2,000 over by addition, and you get 2612 newtons, or 3 significant digits, 2610 newtons of tension in that rock in order to make it accelerate upwards. Okay, so that's our first dynamics problem, and so we'll just mention a few more dynamics problems here. Here's an interesting one. Let's call it the elevator problem. So you stand in an elevator, and the forces that act on you are the attractive force from the Earth, which is always downwards towards the center of the Earth, and then the floor pushes up on you. Now that force, the floor pushing up on you, in physics we call that the normal force. That's the contact force between you and the floor. Now, interestingly enough, if you put a bathroom scale in there, we always say that scales measure the weight, but what they really measure is the force that the floor exerts on you. So scales don't read weight, they actually read normal force. Now, usually in your bathroom, those two are the same. But if you happen to be accelerating, as you would say if you put a bathroom scale in an elevator, then those two forces aren't equal. And we'll do a little experiment in class where we get in an elevator and we watch the reading change, and based on that, and a net force analysis, then we can calculate some interesting things about the elevator. We can find its acceleration. So let's note first that if you happen to be, say, accelerating upwards in the elevator, then an upwards acceleration implies an upwards net force. An upwards net force tells us that the normal force must be greater than the weight. And so if you are accelerating upwards, the bathroom scale will read more than your weight does. So for that case of accelerating upwards, we can say, okay, there's an upwards acceleration. That means there must be an upwards net force, so that the net force in this case, it's always equal to ma. In this case, it's the upwards normal force minus the weight. So that's the net force equation that applies for an upwards accelerating elevator. Now, you don't always accelerate upwards. What if you actually accelerated downwards? So there you are in the elevator, standing on the bathroom scale. The forces that act on you are the downwards pull of the Earth and the upwards push from the floor. So your objective right now is to go through the reasoning and to write a net force equation. Net force is always equal to ma. In this case, what's the net force? So pause the video for a sec and try and fill that in on your own. Okay, so hopefully you reasoned in that moment of individual thinking that because the acceleration was downwards, that implies that the net force must also be down, and that implies that the weight exceeds the normal force, or that the normal force value is going to be a little smaller than usual. So for the net force, we take the bigger one and subtract the smaller one. So if you were accelerating, let's see, so 35 and 2.25. Okay, so you're a 35 kilogram student. The gravity field is 9.8. And you're accelerating downwards at 2.25 meters per second squared. Then this equation would give you the value of normal force, the scale reading that you would expect to find. So let's work out what that is. So 35 times 9.8, 343. And then 35 times 2.25. 78.75. So to find the normal force, well, I'll bring this over here, it becomes positive, and I have to subtract the 78.75 from the 343. And that's 264 newtons. So that would be the scale reading, the Newton scale reading. Now, most bathroom scales, don't read in newtons. The scale reading is actually, although it measures a force, it's scaled in kilograms just by dividing by 9.8. And so this is going to be a scale reading of, well, almost 27 kilograms. So that would be your scale reading. So although the actual mass is 35, when you accelerate downwards, the scale reads less. The scale dropped down to 27 kilograms. Okay, so that's an interesting problem, the elevator problem. Here's another one. I think we'll pick that one up in class. That's the air resistance problem. Let's talk a little bit about the friction problem. So friction, we said, was due to the microscopic roughness and the electromagnetic attraction between these little hills and valleys on the molecular scale. Now, friction resists motion, so that if you're sliding, the force of friction will be opposite to the direction you're sliding. But for powered wheels, if you have a drive wheel, the drive wheel tends to slip backwards on the road, which means that the friction force is actually forwards on that drive wheel. So, and of course, it's that friction force that causes the object to move. The same thing occurs when you're walking, right? When you apply power to your feet using your leg muscles, the feet tend to slide backwards, so the friction force is forwards. It's friction that actually creates that motion. Now, if the car happens to be slowing down, then the drive wheels tend to push forwards on the road, and then friction is opposite to the motion to slow it down. So what does friction depend on? Well, there's a couple of things it depends on. It depends, first of all, on the nature of the surfaces, because some surfaces stick together a lot, like rubber on concrete, and then some slide past each other really easily, say steel on ice. So the quantity that measures surface condition, surface type, is known as the coefficient of friction, and it's a Greek letter mu. So the mu value has no units. It basically just tells us what type of surfaces do we have. And it's a big number, 1 or larger for sticky surfaces, and it's a small number, closer to 0 for very slippery surfaces. So friction depends on the coefficient of friction, mu. The other thing it depends on is the amount of force that's pushing the surfaces together. Now, in many cases, that's just the weight of the object, but not always. Let's consider this simple example. Okay, if the block is just sitting on the surface of your desk, then the force that's pushing the surfaces together, well, it's the weight. But if you come along and if you push down a little bit extra, then we're going to see that there is a lot more friction in that case, because you're squeezing the two surfaces together. But, of course, the weight of the object didn't change. So it doesn't make sense to say that friction is proportional to the weight. But what does change is because you're pushing down so hard, the surface responds with a greater reaction force. So by pushing down, you don't increase the weight, but you do increase the normal force. So we can see in this simple case that it's sensible to say that friction is proportional to the normal force. Now, the normal force in many cases just equals the weight in many simple cases, but not always, as in this case here. So friction is proportional to the normal force, which tells us the amount of force squeezing the surfaces together. So now we're ready to write down our model of friction. As we said, it depends on two things. It depends on the surfaces that are in contact, and then it depends on how much we're squeezing or pushing those surfaces together. Now, friction is in newtons, normal force is in newtons, mu has no units. It's called the coefficient of friction. Okay, so here's a typical friction problem. So we're pulling a block across the surface, and here is the mu. This is the coefficient of friction with no units. And we want to start by drawing a force diagram. So we'll draw all the forces that act on the object. Okay, so one force is clearly already indicated. There's 20 newtons there. There's also going to be a weight force and a normal force. And then we're pulling it to the right, friction will resist that. Friction will act to the left. So those are the forces that act on this object. And strip that out of it. Now, let's analyze those forces. So, well, let's label them first. This is the normal force, the weight, the friction force, and this is just the applied force, F. You see there's two parts to this problem, kind of like the consideration that we just gave, where we considered a block and then we came along and pushed on it. That'll be the second part of the problem. Okay, so what can we say? Well, if we do a vector analysis and consider, say, vertical forces and horizontal, or y forces and x forces, in the y direction, or vertically, there's no motion, right? It doesn't move up or down. So there's certainly no acceleration, and that tells us that the net force has to be zero, because they're proportional to each other. And that just says that the forces are canceling each other out, or they are balanced. So that means that the normal force is just equal to the weight of the object. And a 10 kilogram object on the Earth has a weight of 98 newtons. So the normal force is 98 newtons in this case. Now, that's important because it enables us to find friction, because friction depends on the surfaces of contact and how much force is squeezing them together. So this surface is a 0.12 coefficient of friction, and with 98 newtons of force squeezing them together, we can determine how much friction we've got there. So 0.12 times 98, that's 11.76 newtons of friction. So now we can figure out, well, what's the net force? Well, net force is always equal to ma. In this case, horizontally, we've got the applied force F, which is 20 newtons, minus friction, which is a little bit less than 12. So that is the net unbalanced force in this case. So we can solve that for the acceleration. And the mass is 10. And so we see there, so that's 8.14 divided by 10. The acceleration is 0.814 meters per second squared. Okay, so that's our first friction problem. Now, let's change that problem a little bit, okay? Sort of like the consideration we just gave, or the problem we just considered for developing our model for friction. So we're not going to take the same block. We're going to apply the same pulling force, but we're pushing down on this block with an extra force. So it's still the same block, so there's still the same mg force, okay? But because we're pushing downwards, we're going to see that the normal force is going to be quite a bit bigger than it was before. And because the normal force gets bigger, then so does the friction force. And then that's going to change the acceleration. Okay, so if we complete this force diagram here, this is Fn, this is the applied force, this is the weight. The weight doesn't change, it's still the same object. This is the friction force. What are we going to call this? I guess we can just call it, I don't know, force of push or something like that. So the analysis is similar in the vertical direction because it doesn't move, there's no acceleration. The forces have to balance, but now there's three forces in the vertical direction, so the forces balance up and down. The only upwards force is normal force, but there's two downwards ones. There's the push and the weight. So because you're pushing down with 15 newtons, the normal force is bigger, and this is what we said earlier. So pushing down makes a bigger normal force. Well, because friction's proportional to normal force, now we're going to have more friction. Let's continue with the analysis. Horizontally, friction is mu Fn. It's the same surfaces, 0.12, but now normal force is bigger, so that means friction's bigger too. 13.56 newtons. Now, the net force is still the pulling force minus friction. The pulling force is still 20. But because of the downwards push, which increased the normal force and increased the friction, now the acceleration is smaller. So there's a lot of good things introduced in this example. First of all, it's a good friction problem. It shows us that friction changes in variation or in proportion with the normal force, not in proportion with the weight. It's more practice writing net force equations. And then lastly, it shows us that the same sort of analysis we did with projectile motion, where we considered vertical and horizontal components, x and y components, we're going to use that again in dynamics. We're going to consider forces that are in the y direction and forces separately that are in the x direction. And those two directions, once again, will be independent. So there's an introductory look at some dynamics problems, and we'll talk about these and practice some more of these when we meet together in class.